Hello, Chem 2 students. Mr. Keister here with you again. This is the video for Friday, September 18th, 2020, which is our scheduled 21st day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons. However, the lessons and the order of those lessons will remain the same regardless of that. So let's take a look at today's do-nows and see what the schedule has for us today. Today you're to pick up page 37 over nuclear equations. Yesterday you picked up the notes for Unit 2.2 over nuclear chemistry and the initial assignment that went with that. That assignment is due right now. It should be here in class. Of course, it should be turned in by the tardy bell. If you're at home, that should be submitted by the time your class normally begins, had you been in schools. Make sure you submit that electronically on time. You can check your answers, of course. If you're here in school, they're on the board. If you're at home, they are located on the answer keys page in Canvas. Today we're going to start the Unit 2.2 notes packet on nuclear chem. We'll briefly go over some nuclear discoveries, the different types of radioactive decay, and then go on to the nuclear equations. There'll be an assignment over this that is due Monday. It's this assignment right here, and I will be collecting it for a grade. Your next online homework assignment, 2.1 atomic structure, is due Monday morning at 7:30, so don't forget about that either. So let me head to the board here, and we'll get things rolling. And there we go. All right. I think that looks about right. All right. So we're going to begin talking about electromagnetic radiation, which is where nuclear chemistry comes from. And so we're going to be spending a lot more time on this again in Unit 3. So this is just kind of the intro to that, and then we're going to hit it again hard in the next unit. So high energy particles that have no mass and are given off by different objects are called electromagnetic radiation, or EMR. Okay, EMR moves through space as packets of energy that are called photons. All right, and each photon has a certain quantity of energy that is characteristic of that particular type of radiation. So when we hear the term radiation, it doesn't necessarily mean that the energy associated with that radiation is dangerous to us. Some are, some aren't. Okay? The different types of EMR are determined by the range of energies given off by each. They're laid out in order, and the entire range of energies given off by EMR is called the electromagnetic spectrum. So here I've got a little diagram of that. The spectrum shows the different types of EMR and the relative amount of energy that each gives off. Let me raise this up just a little bit. So as you can see here, increasing energy from left to right, radio waves, television waves, microwaves, infrared rays, the visible spectrum, which of course is light, and then ultraviolet or UV, X-ray, and gamma. Notice I have a little line here. This is the cutoff between what we call non-ionizing radiation and ionizing radiation. Non-ionizing radiation does not have sufficient energy to cause mutations in cells and cause living matter any harm. It doesn't mutate the cells and make them start going crazy, which is what cancer is actually. And so these types of EMR are non-ionizing. Their energy is not sufficient in order for us to be concerned about them. They're around us. It's going around us and through us all the time with no ill effects. These three, however, UV, X-ray, and gamma, are a much higher energy radiation. And again, as you go this direction, they get increasingly energetic and increasingly dangerous then, of course. UV, of course, we associate with the sun. It's a main source of UV. X-rays, of course, probably most all of you have had one of those. And gamma rays are very, very high energy radiation. We'll be talking about gamma rays here again in just a few minutes. So non-ionizing radiation is not harmful to humans and is found from the visible spectrum on down to radio waves. This form of EMR transfers its energy to matter and is not harmful to humans or other living cells unless they're exposed to it at an intense level or for an excessive period of time, which under normal circumstances is never going to happen. All right? Ionizing radiation, though, which includes all nuclear radiation, such as alpha, beta, and gamma particles, plus other high-energy EMR, like we mentioned, UV and X-rays, has the greatest energy and potential harm to humans and other living cells. It's more greatly concentrated and can cause severe damage to living tissue in a relatively short period of time based on the type of EMR. Nuclear radiation results from changes in the nucleus of certain atoms. Some atoms have an unstable nucleus, which we call radioactive, which is a nucleus that can spontaneously change to the nucleus of a totally different atom. It gives off that extra energy so it can stabilize. Okay? And when it does that, we call that radioactive decay. And it usually results in the production of the nucleus of a different atom, a smaller one, an ejected nuclear particle, usually one of small mass, and then, of course, energy, which then allows it to stabilize. So if we have a radioactive nucleus, it undergoes decay, right? It undergoes decay, and then it emits a new nucleus, a smaller one, some type of ejected particle, and energy. And these three things together are what we call nuclear radiation. I want you to realize that the term nuclear energy or nuclear radiation is named aptly because all of this stuff happens or originates in the nucleus of atoms, right? In the nucleus. Okay, so you were to watch some videos over these scientists, maybe a few others, prior to today's lesson. I hope you did. The videos were quite short and also very informative. I mean, I have a few notes here on each of these people. We're actually going to look at one of the videos because it's so important to the study of radiation. We're going to look at one of them, but I'll just briefly go through each of these. And hopefully you watch the videos. If you haven't yet, please do. They will certainly give you some a little more detailed information, help you understand what the contribution was of each of these scientists. So Röntgen discovered X-rays. William Röntgen, German, discovered X-rays when he saw that certain minerals glowed or fluoresced when hit by a beam of electrons, which were provided by an electric current. He is the discoverer of the X-ray. All right. Further experiments showed that X-rays couldn't pass through dense materials such as lead and bone, which is why they're so valuable as a medical diagnostic tool today. So when an X-ray passes through you, it goes right through the skin, right through the tissue, till it gets to the bone, because those aren't very dense. When it gets to the bone, which is very dense, it can't penetrate that bone, so it bounces back or reflects. And it's that reflection is the picture that showed up on the X-ray sheet itself. Okay. Becquerel discovered radioactivity by accident when he placed a fluorescent mineral containing uranium along with a photographic plate in a drawer. He was a photographer as well as a scientist. And those of you that, well, you're probably not old enough to know this, but back in the old days, we actually had cameras, not phone cameras, but cameras that used film. You put the film in, took pictures. When you took the last one, you took the film out, took it to the pharmacy or wherever, and had it developed. Well, that film, one of the first things you learn when you had your first camera is that you never change the film in your camera in direct sunlight. You usually pull the shades or pull the curtain shut, darken the room. And the reason for that was the UV radiation that comes from sunlight would affect the film, right? It would expose it, basically, and cause it to undergo a change, and thus ruin the film, and you wouldn't be able to take pictures with it. So that's basically Becquerel when he discovered radioactivity, and he was studying radioactive elements, radioactive matter, and when he placed this mineral in his drawer where he kept his film, next morning he opened the drawer, the film was ruined. And well, there must be something in this mineral similar to what there is in sunlight that would cause that to happen. And the similarity was they both contain ionizing forms of radiation. Okay. The Curies, Marie and Pierre, studied uranium ore and discovered that not only uranium but two other elements unknown at the time, radium and polonium, were also in the ore. Marie Curie, of course, is a key figure in the study of nuclear science. She was ahead of her time, and unfortunately, she did not get the recognition she deserved initially, just because she was a woman. All right, but she was brilliant, pioneer. They studied uranium long before the dangerous effects of it were fully known. They didn't protect themselves like we do when we get an X-ray. You get an X-ray, you go, you wear a lead covering, except for what they're going to X-ray. The technician goes behind the wall. They don't stand there in the room. And it doesn't last very long, all right? Well, that's because you're getting dosed with some high-energy radiation. Well, they work with this stuff with not much protection over long periods of time, and both of them actually suffered from radiation sickness. And Marie Curie died from it. Her husband did not. Kind of a weird story there. He actually got run over by a horse and buggy one night as they were coming out from going to dinner, I believe. But he also had radiation sickness, but she eventually died from it. Albert Einstein in 1905, of course, we all know E equal MC squared. He was a big part of this long list of people that contributed to nuclear theory. He was the first one to really understand that there was an immense source of power within the nucleus of radioactive atoms. That energy, those unstable atoms that want to release energy, if we release that energy all at once, then we're looking at an immense source of power. We use nuclear power yet today in nuclear reactors to produce electricity. In that scenario, that energy that's being released by the radioactive isotopes, radioactive atoms, is controlled. In a nuclear explosion, of course, that energy is released all at once. That's really basically the only difference between the two. Okay. Rutherford. We're going to watch Rutherford's video. Rutherford, of course, we've talked about already, the father of nuclear science. We recall that he discovered the nucleus and the proton based on his gold foil experiment. If you recall, he did that by shining alpha particles or running a beam of alpha particles through a piece of gold foil. The reason he reason he was able to know how to do that is because of what he did prior to that in his work with radioactivity. All right, and we're going to show that video here shortly, just because it was so influential in the study of radioactivity. He actually discovered the three basic types of radioactive particles. Okay, alpha, beta, and gamma. In fact, let's just go to that video right now. It's not very long, and let's talk about the significance of his discovery. Okay. And I may stop this partway through and make a couple of points. So,
British scientist Ernest Rutherford was one of the first to show that radioactivity could consist of three distinct types of radiation. The three types differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck.
Okay, so this is very similar to what he did in his gold foil experiment. his source of radioactivity was actually uranium, and so he had that in an enclosed box, so to speak, with an opening on the end, so the radiation would only escape out of one end. And so then he focused that radiation through this slit, which concentrated into a smaller beam. And then as it struck a phosphorescent screen here, it's much like an X-ray, all right, it would glow or fluoresce because of the amount of energy associated with that radioactive beam. So let's go on and see what he discovered.
In the absence of an electric field, all the radioactivity beam strikes the target at a single point.
Right there.
When an electric field is applied, the initial beam is separated into three components.
Okay, here's the key to his experiment right here. So when he put two electrically charged plates here, of course, one's charged positive, one is negative, and that beam passed through there, now all of a sudden it wasn't showing up on the screen as one beam, it was showing up as three. Now let's think about that, all right? So here's the positively charged plate, all right? So something that is, as it passes through, it's being subjected to a force. Remember a mass spectrometer? The particles were subjected to a magnetic force. Here the particles, the radioactive particles, are being subjected to an electric force, right? Force is a force. Of course. So anyway, the particles that came towards the positive charge had to be charged out. What's attracted to positive? Negative, all right? These are negatively charged particles. Some of the particles went down this way. Well, they were attracted to the negative. What types of particles are attracted to negative? Positive particles, okay? And then these went right straight through. They weren't affected by the electric field at all, which means they weren't charged at all. They were neutral. So in this beam, this radioactive beam, there were actually three different types of radiation, three different types of particles. Negatively charged ones, neutral ones, and positively charged ones. And the other thing is this. Remember in a mass spectrometer, the more massive particles did not deflect from their normal path as much because they have greater inertia. Well, look here. The positive particles here did not deflect nearly as much as the negatively charged particles did here, which means what? It means they're more massive. So these were the heaviest particles. These were much lighter, and of course these are uncharged, all right? And again, went straight through, so they weren't affected by this electric field at all. So there were three distinct particles that Rutherford discovered were a part of radioactivity. And he then used a source of the positive particles, which we're going to soon learn, or if you don't remember already, are alpha particles. He used those particular types of particles to confirm in his gold foil experiment that the nucleus contained positively charged particles. So his work on the theory of the atom, on atomic theory, was directly related to his previous work in his study of radioactivity. So let's go on and finish this, and then we'll come back.
One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays. Other experiments showed later that the beta rays are actually high-speed electrons. The alpha particles proved to be helium nuclei. The gamma rays are high-energy photons, analogous to X-rays.
Okay, let me cut that off. As I've said before, and I'll say it again, Ernest Rutherford wasn't called the father of nuclear science by accident. He earned that title. And we're not done with Rutherford yet. He did more, believe it or not. Now we work our way towards the mid-1930s. Now we're taking Einstein's theory that perhaps we can harness all this energy that is released naturally from radioactive elements and harness that energy for some purpose. Well, what purpose was it? Well, in the 1930s, of course, Hitler comes to power and is reinvigorating Germany after their defeat in World War I. And they're wanting to get some revenge on the rest of us and exert their domination over not only Europe, but the entire world. And so this, as you can see, Enrico Fermi was an Italian. He worked under Mussolini, who was another dictator that was associated very closely with Hitler. Lisa Meitner, Otto Hahn, and Otto Frisch, all Germans. All right. So all this research began in Germany and Italy with the creation or the thought behind it, and then the ultimate development of the creation of atomic weapons. In the early 40s, at the urging of Albert Einstein. Now, Einstein is a German too, but he was also Jewish, and he saw what was going on, or what was going to happen with Hitler's coming to power in Germany. And so he and others, including Enrico Fermi and Lisa Meitner and others, all defected to the United States in fear for their lives. And so had that not happened, and the development of atomic weapons forged ahead here in our own country, and we didn't get to the development of the atomic bomb before our enemies did, things might have turned out very differently in World War II. It's kind of something strange to think about. But anyway, in the early 40s, at the urging of Einstein, for fear of being beaten to it by the Germans, President Roosevelt initiated the Manhattan Project, which was led by J. Robert Oppenheimer. Einstein was asked to lead that project. He declined. He said he would be an advisor, but he was not in favor of actually using an atomic bomb. He knew what it was going to do, knew how many people it was going to kill, and how many people it was going to infect with radiation sickness. He wanted to develop the bomb to use it as a deterrent, all right, so that we would not use them at all and force other countries to not develop them by saying, hey, we've got this. If you don't want to have one of these dropped on your country, then, let's all set aside and stop this. That's what he wanted. Unfortunately, the way the war was going, things didn't turn out that way. And the Manhattan Project, of course, ultimately led to the development of the atomic bomb, and not only for its just to have it developed, but to actually use it. Of course, we dropped 2 of them on Japan, which was a terrible, terrible thing. Many people lost their lives, and many others suffered from radiation sickness for years afterward, and ultimately many of them lost their lives too. But the thought behind that was the war wasn't going well, and hopefully that this would bring it to a quick end and ultimately save even more lives. And I guess it just depends on how you look at it. The war did come to a very quick end after that, so I guess that was good. But, that is still being argued today. Fortunately, we've never used them again. They still are in the news now and again, more recently with North Korea. And so the nuclear threat, I guess as long as there's going to be people fighting about something, the nuclear threat, I guess, is still going to exist. So it's just something we've got to deal with. So anyway, let's go on to the next page here. Okay, let's look at the different types of radiation. And again, Rutherford is responsible for this. So alpha particles were shown to be charged positive, okay? gamma rays were the neutral nuclear particles, and again, very high energy. And the discovery of radioactivity again proved that there were subatomic particles within the atom that provided these positive and negative charges. All right, and so this soon led to discoveries of the electron by J.J. Thomson, of the nucleus and proton by Rutherford himself and his co-workers, and then the neutron later on by James Chadwick. All right, so let's look at decay. So the average element has approximately 3 isotopes, and about 1/5 of them are radioactive. We call these radioisotopes. Naturally occurring radioisotopes emit background radiation, which is low energy, non-ionizing, non-harmful. It is all around us all the time, but it doesn't affect us negatively in any way. There are several different types of radioactive decay. And the first is alpha decay. And again, an alpha Rutherford discovered all of these. An alpha particle is the same size as the helium nucleus, 2 protons, 2 neutrons. And it's written as either 4,2 alpha, that's the Greek letter alpha, or 4,2 He. Okay, 4 being the mass number, 2 protons plus 2 neutrons, 2 being the atomic number, being the number of protons. All right, so a quick point here, either of these is correct. The helium notation is used more often. I don't care which one you use, but I will tell you this. Mastering only uses the helium notation, 4,2 He. So make sure you remember that when you're doing your mastering assignment over nuclear. Okay. Alpha particles are released by high mass elements above atomic number 83. So these come from big alpha is the biggest nuclear particle. It comes from big elements. All right. Those that are proton rich, lots of protons. Since it contains no electrons to balance the 2 protons, alpha particles have a charge of +2. All right, +2. Alpha particles' large mass, they're the largest of the nuclear particles, can cause great damage to human tissue, but only over short distances. Air will stop it over just a few centimeters, and skin will block it entirely. So unless you are standing right next to an alpha radiation release whereby you can breathe it in, you're not going to get it. All right, you're not going to get it. But if you do get it, it's extremely dangerous. All right, extremely. Beta decay. All right, so a beta particle is a fast-moving electron, but it's emitted from a nucleus, a radioactive nucleus. This is not an electron that encircles the nucleus in the electron cloud, like a normal electron. We'll get to that here in a second. So this is the Greek letter beta, all right? And it's written, its notation is either 0, -1 E, or 0, -1 beta. The -1 shows that it has mass. That's why its atomic number is listed as 1, although it's very small. But the negative sign is used to show that it has a negative charge. All right. Now again, I don't care which one of these you use, but the 0, -1 E notation is the one that mastering accepts. So when you're doing your mastering, make sure you use that one. Okay. So beta particles are emitted by neutron-rich. They have lots of neutrons, unstable nuclei. They are high-energy electrons, but they are not electrons from the electron shells, just like I said in the electron cloud. Instead, they are electrons that are generated in the nucleus when a neutron splits to form a proton and an accompanying electron. All right? Like electrons in the electron shell, though, in the electron cloud, beta particles also have a -1 charge. Okay? -1. Now, beta particles travel at very high speeds, and so they can travel long distances, very unlike alpha particles, and they can penetrate the skin easily, again, unlike alpha particles. However, they are far smaller than an alpha particle, and so they're not as damaging to human tissue. The bigger the particle, the more damage. I mean, think about it. Would you rather get hit in the arm by a ping pong ball or a bowling ball? Same thing here. The larger the particle is, the more damage it's going to cause. Okay? So just remember that. Positron, so it's not as damaging as alpha because of its size, but it is dangerous because it can get inside you easily. Okay? Positron emission is another form of beta decay. The positron is the antimatter equivalent of an electron. It has the same mass as a beta particle or electron, but the opposite charge. So it's written as 0, 1 e, all right, not -1, that's a beta particle, or 0, 1 beta, all right, or 0, 1 beta. Again, mastering does have its preference, and let's make sure you note this. Mastering uses the 0, 1 e. However, they want a plus sign in front of the 1. So to distinguish it fully between it and a beta particle. So remember when you're doing mastering to put the plus in front of the 1. So it's 0 plus 1 e. I don't care which of the three you use on any work you do for me. All right, but mastering, make sure you put that plus sign in there. Gamma particles or gamma rays are, of course, high energy radiation. They're the most energetic of all types of EMR. They do not have any mass whatsoever. They are pure energy. So alpha, beta, positron particles have mass, all right? Gamma does not. It's pure energy, all right? This is the Greek letter gamma, okay? 0, 0, or just gamma. I don't care which one you use, but again, mastering wants the notation to include the zeros. All right, so make sure you remember that. Gamma rays are electromagnetic waves of very short wavelength and very high frequency and very high energy. They're emitted by most radioactive sources along with alpha or beta particles. So if you're releasing alpha or beta, chances are good it's releasing gamma too, which is the energy part of the nuclear radiation. After alpha or beta emission, the remaining nucleus may still be in an unstable energy state. By releasing a gamma photon, it then drops down to a normal, or what we call the ground state, where it stabilizes. So gamma rays have no charge, as Rutherford proved, associated with them. Gamma can also travel long distances, just like beta can. They're the most penetrating. It's pure energy. There's no mass involved at all, so they just go right through. But they're not quite as damaging as alpha particles. They are high energy. They're extremely dangerous, but they're not as damaging as alpha particles because, again, alpha particles have such a large size. However, when taking all factors into consideration, they are the most dangerous of all types of radiation, right? That would be gamma, okay? All right, let's see, next. Oh, I know what I wanted to mention. One other thing. Put a little star down here and fill this in. All right, neutrons are also involved, right, in many nuclear reactions. All right, neutrons are also involved in many nuclear reactions, especially ones that involve the splitting. That involve the splitting of larger radioactive nuclei. We use neutrons to split uranium nuclei in a nuclear reactor or in a nuclear device, a nuclear bomb as well. And so you need to know how to write a neutron properly, its notation. It's a small letter n, not a capital N like nitrogen. And then, of course, a neutron has mass, and so its mass number is 1, but it has no protons associated with it. So its atomic number is 0. So it's 1, 0, N. All right, 1, 0, N. All right, let's look at some nuclear equations, and then we'll be done for today. So the key in balancing a nuclear equation is that both atomic number and mass number are conserved. It's conservation of mass. All right, conservation of mass. So here's an example of alpha decay or alpha emission. Notice that an alpha particle is found on the right side of the equation, on the product side, because it is being released. All right. So here's your alpha particle. This is radium-222. All right, 222 over 88 Ra is radium-222. Okay, so what else is ejected here? Well, the mass numbers have to be equal on both sides of the equation. Here you have 222. Over here you have 4. The remaining mass number that would make those equal would be 218. Do the same with atomic number. 88 on the left, 2 on the right. Means we're left with 86. And atomic number 86 is how we identify the element. That would be radon. Okay? So again, 218 plus 4 is 222. 86 plus 2 is 88. Conservation of mass. Okay? Here's a beta decay or a beta emission. Again, a beta particle would be found on the right side or the product side of the reaction because it has been emitted or released. Here we have thorium-234. So we have a mass number 234. The beta is 0, and so our missing mass number is 234. Here we have atomic number 90. Here we have -1. Be careful with this one. So what plus -1 is 90? Well, that would be 91, all right? And atomic number 91 is protactinium, or Pa. So again, 234 plus 0, 234. 91 plus -1, 90. Conservation of mass. Here's a positron decay. All right, so here we have 40 and zeros. Missing mass is 40. Here we have 19 and 1. The missing mass then, or the missing atomic number would be 18. And atomic number 18 is argon. So again, 40 plus 0 is 40. 18 plus 1, 19. Okay? And then here's gamma decay. So here's gamma, 0, 0. No mass. All right? No protons, no neutrons, no mass. Notice there's a 2 there. Well, that's because there's 2 of them released. How do we know that? Because of the amount of energy that was released. All right? Gamma has a certain amount of energy associated with it. If twice that amount is released, 2 gammas. All right. So this is uranium-238. This is thorium-234. So we have 238 on the left, 234, and 2 times 0, which is still 0. So the missing mass is 4. Here we have 92. Over here 90, and again 2 times 0 is 0. It's 2, and that of course is an alpha particle. All right, that's an alpha particle. So alpha. But I want to remind you of something else. Remember up here, thorium-234 is also radioactive, and it will spontaneously decay, just like it did up here, and release a beta particle and a 234 protactinium. So now look, with uranium-238, you release gamma radiation, you release alpha radiation, and ultimately you release beta radiation. So uranium-238 produces all 3 major types of radioactive particles. Okay? All right, so let's look at some examples here and we'll be finished. Again, we're just going to utilize conservation of mass to figure out what's missing in these equations. Excuse me. So the first one, we have lithium 6, and here's a neutron. All right, 1, 0, N. Lithium 6 plus a neutron yields an alpha particle plus what? Well, let's look at the mass numbers. So we have 6 plus 1 is 7 on the left, 4 on the right. They got it equal out. So the missing mass number is 3. Our atomic numbers, 3 plus 0 is 3, 2 over here. Missing atomic number is 1. Atomic number 1, of course, is hydrogen. This is hydrogen 3, which, if you might recall, is also called tritium, which is also radioactive. Okay? Next page. So our unknown is here on the left. We got hydrogen 2, deuterium here. So over here on the right, we have 61 and 4, 65. 2 on the left. What's missing then would be 63. Atomic numbers, 28 and 2 on the right, which is 30. Minus 1 is 29. Atomic number 29 is copper. Okay? Here's carbon 12 and hydrogen 1. So 12 plus 1 is 13. Over here, our mass number is 13, so the missing mass is 0. 6 and 1 is 7. Over here is 7. 0 again. All right? That would be a gamma particle. All right? A gamma particle. 0, 0 is gamma. Next one. Americium 241, Neptunium 237. The difference there in mass number is 4. 95 minus 93 is 2. And again, that would be an alpha particle. And again, you could write it with the alpha sign too. I don't care. But remember, of course, mastering, you need this. Next one, lead 214 and bismuth 214. Mass difference there is 0. 82 and 83. Okay, that's going to have to be negative 1. Remember, negative 1 plus 83 would yield 82. So that, of course, is a beta particle. And again, you could write it using the beta symbol. I don't care either way, but mastering requires the E, so make sure you remember that. Zinc 64 and a beta particle. 64 and 0 is 64. 63 over here, so there's a difference in mass of 1. 30 plus negative 1 is 29. We already have 29 here, so that's 0. 1 over 0 is a neutron. And then finally, the last one here, carbon 11, 11, 6. So 11, and over here, boron 11, the masses are the same, so that would be 0. 6 here and 5 here, difference there of 1. Okay, so 0 over positive 1 is a positron. Again, which you could also write 0, 1, beta. Either way. Remember, though, in mastering, they want a plus sign in front of that 1 using this notation with the E. Don't forget about that. I want to show you 2 other things real quick before I sign off. Let's say you're doing one of these and you're figuring out the missing numbers, and you come up with this. 0 over negative 2. And then, well, wait a minute. There is no such thing as 0 over negative 2. But what is something that we do know about that's very similar to that? Well, 0 over negative 1 is a beta particle. How could we get from this to this? Well, there would be 2 of them, right? 2 beta particles would result in an overall mass number of 0 and an overall atomic number of negative 2. So keep that in mind if you run across something like that. Here's another one, 3, 0. Well, we haven't discussed anything that's 3, 0. But remember, a neutron is 1 over 0. All right? How can we get from 3, 0 to 1, 0? Again, we could do that by the emission of 3 neutrons. 3 times 1 is 3. 3 times 0 is 0. So if you run across a situation similar to those, I think now you should know what to do with it. Okay? That finishes us up for today. You have a nuclear equations assignment to complete for tomorrow. I am collecting that assignment. Actually, it's for Monday, sorry. and I am collecting that assignment. It shouldn't take you long. It's just a matter of using the conservation of mass, balancing the mass and atomic numbers, and figuring out from those numbers what the missing particle is. Okay? So until next time, this is Mr. Keister signing off. Everybody stay safe, keep working hard, and I'll catch you next time. So long.